So pretty much all we went through yesterday was looking at a little bit of history, which you'll see probably at least one question on that. And then the decay processes, our new notation for looking at nuclear processes on what's happening with them, balancing those equations and what the different particles were in each of those radiation forms. So we've got our alpha, beta, and positron, where we're looking at a loss of something from our nucleus. Then we also have our gamma radiation, and our gamma radiation is just an energy loss. So it doesn't carry any mass or charge. It just has a massive amount of energy. And then we've got electron capture, which is actually the absorption of a low-level electron into the nucleus. Okay? So you're responsible for what each of those symbols mean, understanding the mass numbers, charges, all that kind of fun stuff. Remember the charge that we're showing in the lower left-hand corner is the charge on what? It's the charge of the protons because it's the charge of the nucleus. It's not the charge of the atom, but our nucleus. So we don't worry about the electrons. Okay? And then we kind of ended on the manipulations on what we can end up doing with this. So when we first approached balancing the equations, we just looked at the loss of these different particles, how that affects the overall structure, and that kind of fun stuff. We can take this further if we go up into the much larger scales, and we can do atom smashing. So we can take different atoms and smash them against each other. And in the process, we run the possibility of being able to generate new atoms. Okay? And that's where we get into the transmutations. So we force different nuclei at very high speeds to hit each other, and then we hope once they hit an impact that we can get them to form a new larger nucleus. Okay? We'll look at an example of that in just a second. The other options are radiometric dating. So now we're bringing in time as a consideration, which goes back to kinetics. So we're going to look at first order kinetics as it comes, or as it relates back to radiation. We'll talk briefly about a Geiger meter and how we can detect different forms of radiation. In most cases, what we're looking at there is just introducing a new unit, so that when we report our radioactive specimens, we're talking about the ways that we monitor them or their effective concentrations. So it's ultimately all we're seeing out of that is a new unit show up. And the very last thing we'll look at is how it can be a source of energy, okay, both in the form of being useful, if we look at our power plants, and destructive in nuclear bombs. Okay? I'll leave you to kind of read up on a lot of the kind of background information behind how we're using nuclear plants and how bombs are useful, or not useful, destructive. There just isn't a whole lot I can put together on a slide and then teach you about it just reading. Okay? So read through the textbook on those to give you kind of more of a background behind that. So when we look at transmutations, we can take a look at smashing two different atoms against each other. In this case, we can take a beryllium nucleus and a helium nucleus, and if we're lucky, when we smash them together, we generate some products. One of those products happens to be a carbon nucleus, and we also generate a free neutron. Okay? So all we're trying to do is say, okay, we take these two elements, what can happen, or what breaks off? Okay? On an exam, what I would provide to varying extents, I wouldn't expect you, so for instance, I would not say, tell me what the products are when we smash beryllium against helium. Okay? I wouldn't know how to predict that. I don't expect you to know how to predict that either. Okay? So as far as your predictive powers, what I might do is say we smash beryllium against helium and we generate this carbon nucleus. What else was formed? And you would have to predict that that neutron was also left over. Okay? Likewise, we could go through and say beryllium was smashed against some atom and generated carbon and a neutron. What is that atom that we smashed it against? Okay? Make sense? So what you're doing is going through and evaluating the different charge changes and nuclei changes. It's just a more advanced application of what we've already looked at. Does that make sense? Okay. Some of the common particles that you'll see in this, protons, neutrons. You'll also see helium nuclei. The other big common one that shows up is deuteron. What is deuteron? You might see it written like this. Where's mass? Mass is the upper left hand, right? What is deuteron? If we take a look at its atomic number, what's the atomic number in this case? It's atomic charge. 1. What element has an atomic or a nuclear charge of 1? Hydrogen. Why do we call it deuterium or deuteron and not hydrogen? What's the difference between this species and hydrogen? If we drew up hydrogen, its atomic number was 1. What's its mass number? 1. How do we know it's 1? We could look at the atomic weight and we see that it comes out as 1. What's the difference between hydrogen and deuterium? A neutron. We just added an extra neutron to the nucleus. That now changes the mass of that element. We have a different isotope of hydrogen. Because it's an isotope that's very commonly used, we came up with a different name for it, and that's where we get deuterium. The other one that you might see would be this one. What is that one? It's an isotope of what element? Hydrogen again. How did we make that? We added 2 neutrons to a hydrogen, our standard isotope of hydrogen, and what we have now is tritium. Okay. You might see these show up in your textbook. That's what they're referring to. The other ways you might hear them referred to as heavy hydrogen. Sometimes you'll hear the phrase heavy water. Why are we saying it's heavy? Because we've added an extra neutron to it, so it's now a little bit more massive, has a little bit more weight. Okay? So you might see these other particles kind of show up in the textbook with your homework problems or in the sapling and connect. Okay? So all you're trying to do is smash these things together. I don't know why we've then decided to adapt this, but if you take a look at that equation, that makes sense. We've dealt with that kind of expression before. Believe it or not, what we've decided to do once we became nuclear chemists is because we decided that we're now fancier and we deal with nuclei, that we need a new way to show balanced reactions. Okay? Again, I have no idea why. So what they've gone through and done is we can actually write our new balanced reaction in a different format. This format down here is saying the exact same thing as this thing up here. Okay? I don't see how it's any easier or faster to write this out than that, but that's the way we do it. Okay? So what does that format mean? Well, we're going to start with beryllium. That's going to be our target, and we are going to shoot it with an alpha particle. So the very next thing in our parentheses. Okay? The next portion within the parentheses is one of the particle products. It's our non-major product. We don't care necessarily about that because it's not very massive. So if we go through it, we've got beryllium hit with an alpha particle. Helium, or helium nucleus is also known as, it's also an alpha particle or alpha radiation. Okay? We also generate a neutron as a product. So we add the symbol for our neutron at the bottom. And then we provide as our very last thing the end result of that transformation. We get our carbon 12 nucleus. Okay? So all we're trying to do is come up with a different format behind saying the exact same thing. You will see this format show up probably both on the exam and almost certainly within your homework. I don't think it's all that important, so you probably won't see it formatted like that very much on the exam, but be aware it will show up. Okay? Questions about that? Questions about the transmutations? All makes fairly straightforward sense? Okay. So now what we've got to do is actually make this a little bit more difficult, because at this point all we really had to do was memorize some stuff and balance equations. Fairly straightforward. Okay? So now what we're going to do is introduce time. One of the important things that we want to evaluate when we look at radioactivity is time, because we're concerned about the safety of radioactive materials. Okay? So if there's an exposure to some radioactive material, we're going to have to evacuate that area. And we would like to be able to tell people when they could come back to that area. Because maybe that radioactive species may be incredibly dangerous, but it's only incredibly dangerous for a day. Well, we can evacuate for a day and then not worry about it. Everybody can come back. Right? If it's instead dangerous for 60 years, then we're going to have to tell everybody that they have to find new homes. We're going to have to do all sorts of refugee transplantation, all sorts of fun stuff to get people out of that dangerous area. Yeah?
Sorry, this is going back to the slide that we just covered.
Yep.
Beryllium, and then in parentheses you see you have the alpha particle there.
Yeah.
But up at the top, you have the helium in the reactant side, whereas yesterday when we covered an alpha particle, you had the helium in the product.
So that was alpha radiation. What is this? This is a transmutation. We're not looking at a radiation. We are smashing two atoms near each other, or two nuclei near each other. It's a different process using similar particles. Does that make sense?
The other was radiation, you said?
Yep. The other one is a natural decay process. The transmutations aren't natural. We have to force them to occur. Okay. So that's kind of our idea behind radioactivity. We're just trying to come up with some way that we can monitor these reactions, just like we did with every other reaction when we looked at kinetics. Okay? So one of the simplifications that we're going to make is looking at concentration. So when we evaluated kinetics before, we looked at concentrations and pressures being our units in our rate expression. So let's actually test you real quickly on that. If we provided a rate expression for a first order reaction, what would it be? What would we start with? I can start with a K. What was that? Anybody remember? Rate expressions. Rate equals our rate constant times concentration of our reactants, and our reactants alone. Okay, this is where they're confusing. We spent over 50% of the semester looking at equilibrium constants, where it's products over reactants. That was capital K. This is a rate constant, which is a lowercase k. When we're looking at our rates, we're only concerned about the concentration of our reactants. Okay, so do not incorporate products into your rate expressions. Okay? So when we did that, we had to look at concentrations, something in solution, okay, or a gas. It's in the solution of air. When we look at radioactive particles, anybody know what phase they're typically found in? They're solids. How can we incorporate a solid into our rate expression if we can only use our rate expressions with solutions and gases? All right, what we have to do is change our perspective on it. When we look at solutions and gases, we're looking at how those particles interact with each other or decompose on their own. Okay? When we're looking at nuclear particles, we're only concerned about the nucleus. So instead of looking at a concentration, what we'll do is refer to the number of radioactive nuclei, also known as, I believe, nucleons. Okay? So we're going to change the perspective on what we're doing with our rate expression. When we look at radiative processes, we're looking at the number of those reactive species. Okay? And we'll have to come up with different ways that we can count that. That's ultimately when we look at Geiger meters. We'll look at a couple examples without counting actual atoms in a second. Okay? Does that kind of make sense? The rate we aren't particularly concerned about. We already talked about the more important aspect when we look at kinetics, particularly as far as radiation goes. We're concerned about time. How do we get time out of our rate expression? What do we have to do? What was that? we have to go back to calculus and we would integrate our rate expression to generate the time-dependent rate law. Okay? So you should remember that from our first order reactions. If we know our rate, we can go through and integrate both sides, and we ended up with that overall expression in the box there. The natural log of the concentration at time t will equal the negative rate constant at that time, plus the natural log of whatever our initial concentration was. All right, well, the assumption that we made when we looked at nuclei is that our concentration is now, instead of being measured as far as the number of molecules per a given volume, we're going to change that to now being the number of radioactive nuclei. Okay? So it's going to be a slight change in our equation. All we're really going to do is change the formatting on this. We're going to change that concentration of A, or the concentration of our reactant, to now being N, where N is the number of nuclei. Look at that, double N. Okay? So what would N sub T be? The number of radioactive nuclei at whatever time we're deciding to evaluate. N sub 0 would be whatever we started at. Okay? So we've got this expression. We can now go through and evaluate it in differing circumstances. When we looked back at the kinetics chapter, one of the things that we looked at was looking at half-lives, or third lives, or quarter lives. So we could go through and simplify this equation, and the textbook does, and it's a very common application when we're looking at radioactivity, because we tend to report things in a half-life. We could go through and then say, well, at the half-life, we know N sub T has to equal 1/2 of what we started with. If we know that, then we can go back through and start subbing this information in. Remember, these were the mathematical equivalencies that I told you needed to understand, so that we could then do these substitutions. If we now go back and substitute in, you'll notice that we can cancel out the number of our reactive particles. And that equation looks pretty nasty, but we can then push it around a little bit more, and we'll find that we can discover that the half-life of a reaction is equal to 0.693 over the rate constant. Okay? So if we know the rate constant for our reaction, we can then determine the half-life. Why is the half-life going to be important? Gives us an idea of how fast the decay process is. So we could then punch in a series of quick calculations to determine roughly how long it's going to take before we hit a certain threshold of reactivity, okay, or radioactivity, which then takes us back to safety. Okay? So our big applications as far as this material goes is going to be using the two equations at the bottom, or actually the equations in boxes. Okay? You're going to be bouncing back and forth between these, either to determine the rate constant or to determine the half-life, and kind of go around in circles between these two equations. Okay? So let's take a look at some examples. So we can go to radioactivity in medicine. It is commonly used in medicine for a variety of reasons. Iodine-131 is used as a, or in fact iodine in general, is used as a contrast agent. Okay? Iodine-131 happens to be radioactive as well. So what we can do is detect for that radioactivity. So if we inject iodine-131 into our bloodstream, there's very particular places that iodine will travel. So what we can do is then say, okay, give it some time to work through the body, and now, okay, now we're going to test you for radioactivity. Okay? And in that process, we can then image where that radioactivity is located or where it's concentrated, and if your body's functioning properly, we'll know exactly where it's supposed to be. If there's something wrong, say you have a tumor, that iodine concentration will vary from a standard state, and we can monitor that variance and say, okay, something's really wrong, we have to do an operation. Okay? So in this case, what is it? It happens that we can use it to image your thyroid gland a little bit better. Okay? So why would we inject this potentially hazardous species into people? Well, it allows us to see things a little bit better, but if we can see things better, that's great, but then we kill the patient, right? So it's not the best option. We could see the thyroid gland really easily if we cut everybody open. Hey, look at the thyroid gland, there's a problem with it. Maybe we should try and say, oh yeah, they're dead now. Okay? So what we want to do is make sure that the contrast agent we use has a minimal, first off, hazard. So we're looking at lower energy radiation. And we would hope that what we're injecting has a very short half-life. Okay, so yes, we are exposing you to now some dangerous particles, but we're hoping is that that decay process happens so fast that you pass beyond the limit of hazardousness, that's a word, right, in a very short amount of time. So we don't have to worry about prolonged effects. And that's usually where a lot of health concerns come in, is the prolonged exposure to anything. Okay? So what we want to go through and do is now evaluate, given this information, the rate constant for the decay, and then ultimately we're going to push it even further, is how long is a patient going to be radioactive after injection. Okay? You'll notice to answer these questions, we're going to have to give you a reasonable amount of material. I'm pretty sure everything I've got in here will be able to get you through it. Okay, so we'll approach this as we go through and carefully piece it together. Yeah.
Just out of curiosity, is that the same stuff they inject in you before you get like a CT scan and all that?
I don't think so. I think a CAT scan is just iodine. It's not radioactive.
Oh, okay.
Yeah. Yeah, that's a fun story too. Because if they inject that, I don't know if anybody's had iodine injected into them. One of the things they caution you about is it feels like you're going to urinate yourself, because as it injects, it causes your body to heat. So yeah, it feels like you're peeing yourself because that area gets really, really hot. It's like, what the heck is going on? It's kind of bizarre.
They use radioactive sodium fluoride these days. It's what it causes you to fast so that the cancer cells will attack the fluoride because it's got a sugar substance to it.
Oh, that's
And
interesting.
much more fast evolving. So
Well, it's going to depend on what you're looking for. So it sounds to me like iodine 131, as far as radioactivity, goes directly to the thyroid. There'll be other agents that they'll add that will target different things depending on what they're trying to find. Okay? Cancer cells tend to be fast growing, so what we want to do is put something in there that we know the cancer cells need. So we can look at sugar substitutes. So we could put in some kind of radioactive sugar, or we could put in something that we know reacts with sugar, because the cancer cell is going to have massive amounts of sugar around it because it needs that energy to proliferate. Okay? So what we're ultimately trying to do is find ways to trick different portions of the body to respond in very particular fashions. Okay? So going through and solving this, what information are we given? We know the third life. So if we came through, so I don't know how much of this I stepped through it, what would we write down as far as a notation for a third life? Third life represents what kind of thing? I know it's kind of an odd statement. What symbol does it represent in our equation? The T, because it is time. So for me personally, I would do T for our time, but I now want to make sure it's not just any time, it's the time for a third life. So what I would do is now say T sub 1/3. Okay, that's just my personal preference. So what do I know T sub 1/3 is equal to? 8.02 days. Do I know anything at the third life other than it's 8.02 days to get there? What is the concentration at the third life? Or the number of radioactive nuclei at the third life? So as far as a notation goes, we could say N sub T, where T is our third life, so I would call this N sub 1/3. What do I know at the third life about that concentration or that number? What's that? It's 1/3 of the original. N sub 0. That is the definition of a third life. Okay? With that information, what can I now do? Do we know N sub 0? No, you actually won't be able to figure it out. Nope. What do you want to do? Let's plug it in. Let's see what happens when we plug it in. Do we even care about N sub 0? So we said the natural log of N sub t, what did you say N sub t was equal to? 1/3 of N sub 0 divided by N sub 0 equals negative kt. What's special about that t? It's the third life. Do we care what N sub 0 is? No, why not? It cancels out of the equation. We don't have to worry about it. And we would get the natural log of 1/3 equals negative k t a third. Do we know what the third life is equal to? Yes? The only unknown? K. What can we do? We can solve for k. We can plug in our third life of 8.02 days, and we can solve for, looks like I did stepwise this nicely, and we can solve for our rate constant. Okay? So all we're doing is plugging in all of our numbers, and we get a rate constant of 0.137 days, inverse days. Okay? Why is it inverse days and not, say, something that we're more used to, inverse seconds? Why did we use seconds when we looked at rates before? The reactions were happening ridiculously fast. Okay? When we're looking at radioactivity, sometimes they're fast, sometimes they're not. We could convert this over into seconds. Does it make sense to convert it into seconds? No, because our number would end up becoming really big. I can't do that conversion. Either it becomes really big or really small, one way or the other. You can figure that out. Okay? So what we'll do is stick with units that are easier to work with. In this case, days happen to be a reasonable number. That's what we were given, so we'll stick with that day unit. Okay? Make sense? Okay. On an exam, or even the homework, more than likely what you would be asked is just question B. How long will a patient be radioactive after the injection? Okay, what are we asking for with that question? Asking for time. To solve for time in this equation, what do I need to know? I would need to know something about the concentrations. What else do I need to know? I need to know the rate constant. So to solve for that time value, I have to go through and solve for the rate constant first, which is why that question was divided out here first. The next part that I would need to know is something about the concentrations, or the number of those radioactive species. That gets a little bit trickier, because at this point, assuming that we are only reading sentence by sentence, we haven't really discussed what the relationship is between those. Right? At no point have we provided what you initially started with as far as the radioactive nuclei, and we don't have really any idea of where we're ending necessarily. Okay? So if we read one more sentence, what does it say? It says we're no longer radioactive when we have 0.1% of the isotope left. Okay? We're also going to assume, for the sake of this problem, that the iodine does not get excreted by the body, right? Which is probably a really bad assumption, but you don't want to involve that rate constant as well. Okay? So what does that tell us? That tells us at whatever our time is, N sub t is equal to 0.1% of whatever we started with. So it's giving us yet another version of what this third life information is. So if we go through and evaluate that, first off, we know our rate constant is equal to 0.137 days, okay, or inverse days. I keep messing that up. And we also know, based on that last statement, that our number of radioactive nuclei at this magic time has to be 0.001 times the initial number of nuclei. Why 0.001 and not 0.1? 0.1 is the percent. We have to convert it across to our decimal value. Okay? With this information, what can we now do? We know n sub t. We don't know n sub 0. We know k. Let's plug in our numbers and see what happens. When we go through and substitute in, what happens to our n sub 0s? They cancel out. Do we care how much we started with? Completely irrelevant. Okay? We can now go through and calculate, punch it into the calculator, and we end up with a time of 50 days. So in the grand scheme of things, our patient is only radioactive for 50 days. Yeah. If we look at a lifetime, that's not too bad. Okay? Assuming I did that math right. Okay? Questions about that? Where these problems are going to come into play is right in this initial setup. Trying to come up with what that expression means, which is why when we talked about it in kinetics, I kept referring back to you need to understand what a half-life meant, because that is what we're translating here. This 0.1%, where did it go? 0.1% is applying to that same knowledge. We have to convert the numbers given into some mathematical expression. Once we've got it into the mathematics, we can then go through and start to solve. Okay? Questions about that? Your frowny face makes me nervous.
When I was putting my numbers, I got 66.
I didn't say I solved it right. Can I take a look?
I just messed up on the negative sign. I got
0.137.
zero, so that's what I did. Zero.
1,
Yeah,
2,
I put
3.
4
Yeah,
zeros.
4 zeros.
Why are the days inverse?
For the rate constant?
Yeah.
So a rate constant is what? Or any rate is a measure of what? What's the rate of your car? What's the speed of your car? What's the fastest you've ever gone in your car?
Is that a
Legally.
question?
Yeah.
Like 75
75 what?
miles per hour?
Miles per what?
Hour? Oh.
Hour. It's a time. When we're looking at a rate constant, it's evaluating that time effect. So we're looking at that inverse. Okay, that's why, oh, and that's not supposed to be a negative there. I should say -1. Whoops, come back here. That unit is also, or is the equivalent of saying 1 over days. Right? Does that make sense? So in this case, our unit of time is days as opposed to hours or seconds or minutes. Okay? Other questions? Okay. Let's see, I don't remember. Is the next one a bunch of problems? So the next big issue that we're going to address here is kind of these new units, or the other common way that we'll see these radioactive times show up, or different radioactive problems. Instead of looking at the usefulness of radioactivity in medicine, we can also use it to time or determine how old an individual compound is. Okay, so that's known as radiometric dating. Okay, and we'll look at a few examples there. So we can do substitution of percents into our equation. We can also do concentration, but when we're looking at nuclei, we can't use concentrations. We have to do a number of them. So then the question becomes is how do we count this number? Well, one way we get around it was using percents. It's just a percent of whatever was there. So we don't have to worry about an exact number. But if you happen to walk up into a site and you want to know if it's dangerous or not, you can't go through and count every single atom, say, at Hiroshima. That's not going to work. we have to come up with some way to be able to monitor that radioactivity or count that radioactivity without counting out individual atoms. Okay, so how do we do that? That's where we come up with Geiger meters, which really should have shown earlier. And what we're looking at in those cases is we've built an instrument that will monitor different radiation signals. And so what it will do is look for the number of radioactive particles effectively. So what we're looking at here is disintegrations per second. So a new unit that we can use for N or even N sub T, instead of giving you molarity or percents or numbers of atoms, we can use disintegrations per second. Where this gets a bit confusing is you now see in there as well a time. That time has nothing to do with our rate constant, effectively. That has everything to do with our N, effectively our concentration of the nuclei. Okay, so just be aware if you're seeing that unit showing up, you're using that as your N sub 0 or your N sub T, potentially. Okay? Because disintegrations per second can be a bit confusing, they went through and came up with a new unit. They named it a becquerel as 1 disintegration per second. Why becquerel? He was one of the original scientists that worked on this. If we look at a particularly radioactive species, the number of becquerels ends up being really, really, really big. And so because of that, we'd end up having to use massive numbers. So just like we did with molecules in moles, we invent yet another unit to represent that large amount. That's where we get a curie. 1 curie happens to be 3.7 times 10 to the 10th disintegrations per second. I can almost guarantee Connect and Sapling will have you use these conversion or use these units to convert between different systems. I won't ask that on an exam because that's 151 unit conversion stuff. I'm not all that interested in it here. I'd rather see what you can do with those. Okay? You will see these units show up in your problems whether or not you have to convert. Okay? So when it comes to the online homework, make sure that you provide your answer in the correct units. Okay? So you have to watch out for your unit answer. Uh-oh. Okay, so what can we do with these different units? There it goes, finally. One of the more common things to do is carbon dating. Okay, so we'll just kind of talk about the life cycle of this. What we end up looking for when we're looking at carbon dating is carbon-14. Carbon-14 happens to be radioactive, and we can monitor that presence of carbon-14 and try and use that to determine the age of an individual species. Okay? To do that, we have to trust that the original source of carbon-14 doesn't change. Okay? So how do we end up doing that? Well, if we go through and look at a natural source, so why would we use carbon-14 to date something? What would we be dating if we used carbon? Some organic material, a tree, a piece of paper, okay, because it's coming from plants. So what we're doing is using it ultimately, or usually, to date the life, or not the life, the time that something was first created, okay, or written. Where that gets a bit tricky is we need to know pretty much our starting concentration of that carbon-14. Okay? Well, it turns out in everyday life, there is natural sources of radioactivity, particularly carbon-14. And if we look at carbon's life cycle, across time, the ratio of carbon-14 and carbon-12 stays constant. Okay? Carbon-14 is constantly getting made, what is it, in the atmosphere, right? Oh, I don't even say it. Carbon-14 is constantly made in the atmosphere by bombardment with ultraviolet light against CO2. So we can convert carbon-12 in CO2 molecules into carbon-14. Where does that CO2 then go? What happens to CO2 once it gets up into the atmosphere? It just stays there? No, what happens to it? Come on, biologies. What was that? Plants consume it. Okay? So if we look at our standard atmosphere, we have a standard percentage of carbon-14 to carbon-12. Plants then consume that carbon. Because carbon-14 and carbon-12 don't have enough of a difference between them, they're consumed equally by the plant. Which means the carbon-14 and carbon-12 percentage in the atmosphere is the same as the carbon-14, carbon-12 percentage in a living plant. What happens to that living plant? It then gets killed, which means it can't consume any more carbon-14 or carbon-12, and it gets consumed by, say, another animal. Okay, that another animal can get consumed by something else. And what we end up finding is that within living things, that carbon-14, carbon-12 percentage stays relatively constant, okay, and it tends to match our atmosphere. What happens, though, if we say take that plant and instead of letting it get consumed, we turn it into paper? Okay, what happens now? Can we get any more carbon embedded into that paper at that individual time that we killed that plant? No. So what happens to the carbon-14? Starts to disintegrate and stop becoming carbon-14. So what we do is we run under the assumption that our ratio stays constant throughout time. And then what we can do is evaluate and compare the carbon-14 left in that, say, paper to the carbon-14 that would be in brand new paper. The difference between that would be related back to the time. Okay? There's lots of error associated with that calculation. So when people go through and do these time calculations, in some cases you'll hear skeptics say, well, there's an error of like 1,000 years. Okay? Which may seem like a lot, but in a lot of those cases where we're trying to date something, we're looking at massive amounts of time. Okay? I don't think the error is that bad. Probably closer to hundreds of years. So if we try and date something to being 5,000 years old, and we only have an error of 100 years, I mean, it's not the greatest, but that's a pretty good estimation, as opposed to just saying, well, it's old. Okay? So we use radiometric dating to help kind of determine and age individuals' items so that we can then say, look, I found the oldest thing on the planet. That kind of fun stuff. Okay? I hope I have a problem on this. Yeah, I did. Good. So we go through and take a look at a cloth sample. It was dated to be 700 years old using carbon-14. Our half-life for carbon-14, there's that 5,000 number, 5,712, 15 years. A fresh sample cloth had a carbon-14 decay rate of 15.2, what is that, BQ? Becquerels, there's our new unit showing up. What was the detected disintegration of the sample cloth? Okay. So here we're not using it to determine time. We're trying to guess what they actually detected as far as the disintegrations go. Okay. So our first step is going to be to try and convert some of this information into something we can use. Okay. So what stuff are we told? What's that? Do we have K? Did I tell you that? Oh, decay rate, yes. All right. So we know our decay rate is 15.2. What is the decay rate? What number in our equation, or what term? That's where we've got to be careful. It's the natural log portion. What we're looking at there is 15.2 becquerels is a fresh sample cloth. So our becquerel unit, we said, was equivalent to the number of nuclei. So our 15.2 becquerels responds or correlates to which unit or which term? N sub 0. That is our initial decay rate, because that's a brand new cloth. Okay? So that would represent what we would expect when we first saw this cloth sample. That is exactly what we would expect to measure. Okay? What else are we given? We're given a half-life. What else? What's that? We're given a time. Okay? But now we have 2 times. Why do we have 2 times? So if we go back to our equation, we're given n sub 0. We're given at least one time, so we got time in there. What are we wanting to solve for? Indirectly, yes. What does the question want? The question wants the detected disintegration of the sample cloth, which means the number of radioactive particles when we measured it, which would be N sub T. What is the sub T? 700 years. So we're trying to solve for N sub T. We know N sub 0, and we know time. Do we know K? No. It's a bit problematic. If we don't know K, how can we solve for N sub T? How many times were we given? 2. Why were we given 2 times? The first time, or one of those times, is going to be able to use to find our rate constant. Which time are we going to use to find the rate constant? The half-life. Because we're given a time and we know something about our concentrations at that. So we'll go through and solve for our K first. To go through and do that, we could go back and substitute in. To do that substitution, remember, what we're assuming, or what we know, is that N at the half-life equals 1/2 N sub 0. We can plug in our substitutions, and we can solve for our rate constant. What do we put in for T sub half? 5,715 years, because we're given the time for our half-life. Okay? So we can do our substitution, and we end up with our rate constant. Once we have the rate constant, now we can go back to solve what the initial question was. We want to know N sub T for this new sample, or for this older sample. Okay, so what we can go through and do, we know K, we know T. Our T in this case is 700 years because that's the age of the sample being tested. And we know our N sub 0 is our 15.2 becquerels. Plug our numbers in. And in theory, we get a decay rate of 14.0 becquerels. Does that number make sense? What do I mean by it doesn't make sense? What can we compare it to try and determine if it should make sense or not? We want to compare it back to the 15.2. Okay? What we're assuming is that this sample is 700 years old, which means if we start at 15.2 becquerels, what happens to the disintegrations over time? Why should it decrease? What happens to carbon-14 when it radiates? It's no longer carbon-14, which means as we pass through time, our disintegrations should drop. Did our number drop? Yes. Okay. So what we could do is now say, yes, that at least makes sense. It's a number lower than what we started with, which does make sense. At least as a first approximation, we've got an answer. Okay? Make sense? Can I say sense some more? Probably. Questions about that? So a lot of these problems are just going to involve substituting in the correct terms. So you're going to have to do some translation, converting that English into the correct symbol for each of these problems. Remember, it can get difficult because we'll throw in percents, becquerels, disintegrations per second, and curies. All of those are ultimately referring back to the same term. What terms are we referring to with each of those cases?
Disintegrations per second.
That's one of the other units, but what value would you substitute? What symbol? Disintegrations per second, percents, we're looking at N, okay, the number of our radioactive particles. So you'll see a variety of different units there. Make sure you translate those units appropriately. Okay? Questions about our kinetics as far as rate constants go? One thing, if you remember back when we talked about kinetics the first time, oh, there it is. That's the equation I was looking for. This equation right here, K equals 0.693 over T sub half. Okay, that is equivalent, I'll write it out. Okay, that equation was something that I said you shouldn't memorize, okay, because it removes your understanding of what's happening. That substitution on what a half-life is. In this case, because radioactivity often is referred to in half-lives or units of half-lives, when it comes to this, solving these for your rate constants, that's a pretty good equation to have memorized. Okay? I don't know if I've got that on the exam. I probably do not, because all it is a substitution of what a half-life means. When it comes to the homework, you can substitute with this directly and get your rate constant very, very fast, as opposed to substituting in all those equivalencies. Okay? How do we end up monitoring these? So this is where we get back to our disintegrations per second, the becquerels and the curies. That comes back to a Geiger meter. So one of the things that they discovered initially was these radioactive particles, when put in a very particular situation, would actually cause electron motions. Okay? So radioactivity could actually cause air to conduct electricity. Kind of a bizarre concept. So what does that mean? Well, we can build a device then to detect the electric current of an air sample. If we put that air sample near a radioactive species, what happens? Now electricity starts to conduct through our equipment, and what do we see? We can now monitor. Hey, there's an electric current. That electric current we then convert back into our units. Okay, so if the electric current spikes by, gosh, I don't know, let's pick some random number. Say a volt. I think that's probably really big, but let's say it's a volt. We can then convert that into a particular disintegration. Okay? So what we can do is count those radioactive numbers and then translate that into our disintegrations per second, then into becquerels, then into curies. Okay? So beyond that, I don't think that's all that important. It's just something that we can use to actually monitor our radioactivity. Okay? That's where our Geiger meters come in. Questions about time? Hi, so the next thing that we've got to cover is energy. What can we do with these radioactive sources once we've got them? We've addressed kind of a safety concern. They could actually hurt us. So we figured out time so we can make sure that we're not in the area when they're hurting us. Now what we want to do is figure out how badly they would end up hurting us, or what's happening with this radiation. What we're looking at is very subtle changes in mass. Okay? Well, as Einstein discovered, our energy, or energy, is related to mass in a very particular fashion. That's where we get the famous E equals mc squared equation. So if we look at a change in mass across a reaction, that change in mass can be correlated to a change in energy for that reaction. So a lot of the problems that you're going to work when it comes to relating to energy is trying to determine the change in mass of an individual reaction and then translating that back to an energy. Okay? So to solve this equation, E should be fairly self-explanatory. We're looking at energy. M is our mass, and C is the speed of light. Okay? Where this gets a little bit more difficult is when we're looking at what units we've got to use for this. Okay? So why is that problematic? Well, what are our units on energy? Typically joules or kilojoules. When we're looking at nuclear radiation, particularly in the version of bombs, we're looking at kilojoule amounts, if not larger than that. If we look at mass, what's our typical unit on mass? Grams. C, what's the unit on our speed of light? Meters per second. So how is mass times meters per second equal to energy? Okay, that direct conversion doesn't really stand out as an obvious relationship. We do see a relationship when it comes back to, I believe it's actually Newton's laws, when we're looking at mass times acceleration. We can generate an energy term, and that's what we've got here. Okay, so what we've got to do as far as our conversion to get our units converted into joules is that 1 kilogram times meter squared per second squared equals a joule. What does that mean as far as our mass? When we go through to solve, the units on the mass must be in kilograms. Okay? Why does this get tricky? When we go back to our nuclear weights or our atomic particle weights, we said we didn't like our kilogram unit because it was such a small number, so we converted it to AMUs. So when we typically look at our nuclear transitions, what's happening? They're almost always reported in units of AMUs. So what do you have to do? Convert to kilograms. Once it's in kilograms, you can then go through and do your actual calculation. Okay? So you have to be very, very careful that you're treating your units appropriately to be able to go through and solve these types of problems. Okay? We don't have to worry so much about the speed of light. As far as accuracy goes with the speed of light, I'm fine with 3 times 10 to the 8. You might check both sapling and connect to make sure you don't get a rounding error, because what's it, 2.98, something like that. So on the exam, I think I've got written on there 3. With sapling, you might see a rounding error if you use 3 versus 2.98. Okay, so be aware of that issue. So let's go ahead and take a look at some practice with this, which I believe might actually be the last slide. Yeah, pretty darn close. Okay, so we're going to look at the decay and molecular weights given. How much energy is released when 1 mole, what does that mean? Yet another unit conversion that you're going to have to watch out for. When 1 mole of uranium-238 decays. Okay, so we're given that equation. We need to go through and figure out what the process is. Okay? So first off, what equation are we going to use? Einstein's favorite expression, E equals mc squared. We could try and calculate the energy of our reactants and the energy of our products and do the difference between them, or we can kind of condense it all into one big thing. Let's see. We can look at our change in energy for that reaction will equal to our change in mass times the speed of light squared. The tricky part of this problem is going to be determining the change in mass. Okay? So, how are we going to do that? How do we calculate any change? What's that? Final minus initial. So we need to figure out what our final mass was, subtract our initial mass to determine the change in mass. The units that were given there, those are 238 AMUs. Okay, so to do this math, what do we need to do? Plug it in and we can get our unit conversion. So we've got a difference in mass, a negative 0.0046 grams per mole. Can we get away with that? I think we can get away with that. I think we can. Okay. We can convert our AMUs over to grams based on that relationship between our moles and our molecular weights through Avogadro's number, and so we know that our change in mass ends up being this value per mole. Okay? What can we do with that? Now that we know the change in mass, what do? Plug it in. Take our change in mass, multiply it by our speed of light squared, and we get a change in energy of negative 4.1 times 10 to the 11th joules. Okay, that's a pretty big number. Okay, what does that number mean? Was energy absorbed or released? How do you know it was released? Because it's a negative number. So in the process of this decay, we've released that much energy. I wish I had something to compare to. I don't have something else to compare to in this case.
Where'd the mole go?
Yeah, that shouldn't have disappeared. Oh, what is going on? Oh. Oh, that's getting worse. Slideshow. Oh, I'm not going to do it that way. Slideshow. Oops. See if I can do it without getting rid of that. That mole unit shouldn't have disappeared. Disappeared, I mean. Yeah. All right. How else can we see this show up? You might see the energy per nucleon. What is a nucleon? Now, instead of looking at converting this over into kilograms here, we'd have to go back to the mass for an atom, not the mass for a mole of these particles. Okay, so you have to be a little bit more careful with your unit conversions and watch out for that. Okay? Questions about it? Okay, so we can end really early if you don't have any questions. I definitely did get some questions about